Alright, gang, here we go. This is for Physics, Unit 7, Part 6. We're talking about standing waves, harmonics. That's what we're focused on. This is for video 1, so this is only going to be the first part of Part 6 in notes. Part 6 is a little bit dense, so we're going to split it into two videos. Okay, so first of all, we're going to split it, or we're going to cover just a little bit of review about standing waves. A couple of videos ago, we talked about standing waves. All right, so remember, standing waves occur when you have constructive and deconstructive interference occurring in the same place over and over and over and over again. And so, and these happen at very specific frequencies based on the length of whatever string you're looking at. This is essentially why different instruments play different notes that they do, especially, specifically, we're talking about strings, so like guitars, piano, so on and so forth, applies here. So this diagram here shows three possible wave patterns, and you can actually have infinitely many of these wave patterns. You just get more of these loops. Now, whenever we're talking about standing waves, we're always going to be talking about loops. Okay, and so a loop is just going down and up and back again. So this would be one loop here. C here would be two loops, 1, 2, and then D would be 3 loops. All right. So the lowest frequency, all right, that produces a standing wave is right here. We define it as F1. Okay, F1, and it has one loop. It's known as the fundamental frequency or the first harmonic. All right, this guy is would be F2, the second frequency, fundamental frequency, or the second harmonic, not fundamental frequency. This is the fundamental frequency. This is the second harmonic, and the third harmonic would be our F3, etc., etc. And we could have a 4, 5, 6, 100. Doesn't matter. All right, so let's think about wavelengths that's going on. So here's our first loop. This is just the snapshot of it. Remember, when we're talking about loops here, we do the upside and the downside because that string, that wave, flips from top to bottom, over and over and over and over and over again. And then, but when we're talking, so here we just took a picture of it, okay? And so here's the snapshot of that single loop. So this wave or this string is experiencing its fundamental frequency or its first harmonic. Okay, so what's the wavelength for this wave? Well, this is only half of a wave, right? The second half of the wave would look like this. So we went ahead and drew it here, and notice that this length here, right from here to here, would be two wavelengths, or this would be two lengths of this string long, because one length of the string only encapsulated one loop here. The second part of this loop would give us the second end of this length. So the wavelength of the fundamental frequency is 2L. Okay, the wavelength is 2L. All right, so essentially the big takeaway here is it takes two loops. Okay, two loops to equal one wavelength. All right, so when we're doing different harmonics, always think about, well, how many loops am I looking at? Divide that by 2, and that's how many wavelengths you're looking at. We need to be able to flip back and forth. So what's its frequency? Okay, well, the frequency, remember the frequency, we can take the velocity of whatever we're talking about is equal to the wavelength times the frequency, right? So this is our standard formula: wavelength times frequency equals velocity, or frequency times wavelength equals velocity. It doesn't matter. So if we're going to solve for the frequency, we would just divide by the wavelengths on both sides. So the frequency would be equal to the velocity divided by the wavelength. And we just said the wavelength was equal to 2L, so we could plug 2L in for our wavelength here. So our velocity is equal to, or our frequency, excuse me, is equal to the velocity over 2L. All right, and so anytime you have a standing wave on a string, you can always find the frequency. If you know the velocity of whatever it is that's going through there, you can just divide that by 2 times whatever the length is, and you can find the frequency of the fundamental wavelength. Okay, so you get this harmonic series here, okay, and so here's the fundamental frequency. It's just one loop, okay. We already defined that its wavelength is equal to 2L, and its fundamental frequency is defined as F1. Remember, F1 is defined as the velocity over 2L. All right, and you can kind of keep going this way as well. Notice that if we divide our in the second harmonic, okay, it's one full wavelength. It fits into L, so our wavelength has doubled. Well, if our wavelength has doubled, that means our frequency also had to have gone down by half, which means it's 2 of these long. So our frequency for the second harmonic is simply 2 F1s, 2 fundamental frequencies put together. All right, and you can see down the frequency part of this, all right, that it follows that pattern, that each harmonic you go down, the frequency of that harmonic is simply the number of that harmonic times the fundamental frequency. So if I tell you that the frequency, the fundamental frequency is like 500 for a specific guitar string, then the second harmonic would occur at 1,000 hertz, and the third harmonic would occur at 1,500, and the fourth would be at 2,000, etc. And you could just keep multiplying 500 by whatever harmonic you wanted to know. Okay, and so notice that, and then the other idea is when we're looking at these strings, in order to figure out what harmonic you need, you just count the number of loops. The second harmonic has 2 loops, 1, 2. The third harmonic has 3. Fourth harmonic has 4. You can have 5, 6, 7, etc., etc. Okay. Notice also that these loops always go in the same pattern. It always goes nodes to antinodes to nodes to antinodes to nodes. You can't ever have 2 nodes back to back. You can't ever have 2 antinodes back to back. It always has to flip-flop between N and A. All right, and then let's look at the wavelengths real quick, because this is kind of where people get tripped up. This one's easy because that's 2 loops. All right, now this guy here, think about this. So the third harmonic has 3 loops in it. Okay, so we've got if we divided this wavelength into 3 parts, we'd have these 3 loops, but only 2 of these guys here, if we drew a line right here, this to this is our wavelength, right, from this to this. So we only need 2/3 of the entire length to reach one wavelength, so we get 2/3 right here. And when we look at the fourth harmonic here, it's split up into 4, and the wavelength here would be down to the middle, right? It would just be half of this. So the wavelength of the fourth harmonic would be half. There would be 2 wavelengths in each L, in other words, okay? So we get this formula here. This is a nice formula, okay? Harmonic series of standing waves on a vibrating string. So if you've got a vibrating string and you're wondering about its standing waves, this is the formula you can use to help you solve for everything, all right? So the frequency of the harmonic, and this N is the number of loops, or the harmonic number. It can stand for either, okay, because those 2 values are equal to each other. All right, the frequency of that harmonic is equal to the number of that harmonic times the velocity of the wave divided by 2 times the length of the string you're on. All right, and remember your N value can be 1, 2, 3, 4, any number, any integer, right, going up. Okay, your velocity is your speed of your wave. It depends on the tension and the density of the string. Okay, so just imagine if you've got a guitar, right? Almost everybody's strummed on a guitar, and it's got those little tuner knobs at the top, tuner knobs. Okay, when you twist it one way, the string gets tighter and your note goes up. Okay, when you turn it the other way, okay, the string gets looser and your tone goes down. And essentially what you're doing is you're changing the density of your string, making the velocity of the wave faster or slower, okay, and so you get a different pitch depending on that velocity. Okay, L is the length of the vibrating portion of that string. Okay, so as you're changing the tuning on your guitar, you're not changing the length of the vibrating portion. Where those 2 frets are at the front and end of the string, the body and then up there on the neck, that distance didn't change, right? So it's still exactly the same. All right, so in order to change the pitch of a string, all you do is need to tighten it or loosen it, okay? You could also just change the length of it. So when you're playing guitar, you could press down a fret halfway down, and you'll be changing the part of it that's vibrating. All right. Now, the interesting thing is, so that's with a string, and we've talked about that before, and it's pretty straightforward. Now, we also need to know about, well, what does it look like to have standing waves in an air column? Okay, so this is like wind instruments, so like pipe organs, you can look at flutes, trumpets, trombones, brass, and woodwind instruments, essentially. Okay, and so these work slightly different, but has very similar characteristics. Okay, so the idea is that you can have what's called an open end, or both ends being open, or one open, one closed. Okay, and so so when we're drawing these, this is your 2 characteristics you want to pay attention to. All right, your air is free to move at open ends. Okay, so antinodes occur. Your air can move up and down. Okay, and so you get an antinode on the open end of your tube, and then on the other end you get a closed end. Okay, and these are the nodes. All right, so depending on if you've got a double open tube or an open closed tube, you can have differences there. Okay, and so the velocity of the wave, all right, is the velocity of sound in air, and so that we define that as 346 meters per second at 25 degrees. So this is the speed, the generally accepted value for the speed of sound at room temperature. All right. So the first one here is when we have both ends open. All right. So there's our formula down here. So notice that we can have different harmonics. And we're going to draw some of these to kind of help us compare them to the string harmonic series. But first I just want you to take a moment and write down this formula. Okay, notice that the harmonic series for a pipe open at both ends is exactly the same as the string. All right, it's the harmonic number, the n value, times the velocity, divided by 2 times the length. All right, and these N and V's and L's are exactly the same. So everything's exactly the same as what we just looked at. All right, but the way these pipes work is slightly different. So let's draw 2 or 3 of these. All right, so we've got, all right, so here is, and you're going to see my artistic ability fall apart miserably. So it's open at both ends. So we already know that means we're going to have antinodes at both ends, right? We just defined that. Okay, now if it's the fundamental, we're going to say this is the fundamental, so we're going to define that as F1. This is our fundamental frequency. All right, so that means we want as little as a wave as possible, but it has to go from antinode to antinode. So that means in the middle we have to have at least one node. So the node is where it's not going to move at all. Right, so there's our guy right there. So we're going from antinode to antinode. Let's see, what color should I do? How about blue? All right, so if we go from antinode to antinode to node to antinode, we're going to start tall, right, and we're going to go through our node, all right, and we're going to come back out the other end at the antinode, and then the other side is going to do the exact same thing. We're going to start tall, go through the node, and then we're going to come up here to the antinode. Now, why is this interesting? Well, let's take a glance at, well, what's the wavelength of this thing equal to? I don't want that weird color. I want my normal color. Okay. And so what's the wavelength of the first harmonic here? Well, the wavelength, okay, well, how many loops do we have right here? Well, we have a half a loop here, and we have a half a loop here. Half plus a half is a whole, so we've got one loop. Okay, so if this is our length from here to here, that means our wavelength has to be 2 lengths long, right? So it would be 2L. Oh, does that look familiar? It's the same as the string, right? Our string had 2 lengths for each wavelength for the fundamental frequency. All right, well, what about the frequency for this guy? Well, the frequency, if we use the formula we just had right there, oh, thank goodness, I thought for a second it would erase that. Woof. All right, so the fundamental frequency, okay, is equal to n times v over 2L. Well, our n is 1, okay? So it's just v over 2L, all right? So that's it. So let's do another one here. So, all right, so let's try F2 here. So we got F2, so we got to have our open pipe here, okay? And we got antinode, all right? But in the middle, we know we can't just do one node because that's going to throw things off, okay? So we're going to have a node and then an antinode and then another node, right? Because it always has to flip-flop between the two. So we'll draw our little dots for our nodes, all right? All right. We'll get our blue color here. So we're going to start tall for our antinode. It's going to go through our node, hit our other antinode, hit our node, and go up here for that antinode. And then we get another one, antinode, go through the node, go up to the antinode, go through the node, come down to the antinode. And so we end up with this shape for our second harmonic. Right? So what would be the wavelength for the second harmonic? All right? Well, the wavelength, well, let's count the number of loops here. Well, the loops, so we have a full loop in the middle. We have 2 halves on the end, so that's 2 full loops. And remember, it takes 2 loops to make a wavelength. Okay, so that means this whole thing is just one wave. Well, that's nice. Okay, so the wavelength of an open tube at the second harmonic is just equal to L. All right, and then the frequency, well, remember, is N times V over 2L. So it'd just be 2 times V over 2L. Well, we could simplify this, right? We could get rid of those 2's. All right, so the V over L would be the frequency. Okay, and so we're so far, and then what else we could, so that's that, but we could also do something a little trickier. So let's do this. We'll do this underneath it. Really, we should have done this from the start, but nobody's perfect. So we have 2 times V over 2L. Now we know that V over 2L is equal to F1. So we can plug F1 into this, right? This becomes F1 right here. So this would just be 2 times F1. So it's the exact same thing. So the frequency of the second harmonic is just equal to 2 times the fundamental frequency. And let's just do one more just to see if we've got it under control here. All right. Now, there's a couple of ways to master these. You can either memorize them using flashcards, but I hate that. I don't like memorizing things. So I'd much rather figure out how it works and then just remember how it works from there. All right. So you could do it either way, whatever you want. So, but as you notice, we've got Anna and then we've got Anna, Anna. So we've got to have an Anna, Anna, Anna here, right? So we're going to have a node right here. We're going to have an antinode, and then we're going to have a node in the middle. We're going to have an antinode, and then we're going to have another node. All right, notice that I'm not very good at spacing these things out. So here's our node, here's our node, here's our node, like so on and so forth. All right, notice that it's got 3 nodes. Where's my ink color? My blue. Okay, so we got our antinode up here. Comes down, comes down through my node, hits an antinode, hits a node, hits an antinode, hits a node, and then an antinode. All right, and then we do the same thing here. Boom, 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 boom. All right. All right, so that's pretty exciting. So our wavelength here, all right, so the wavelength of the third one, well, let's talk about how many loops we have here. Now, you should be able to see the pattern now. We've already done this. It just looks more complicated because the loops split up, right? But how many loops do we have here? Well, we have 1, 2 full loops in the middle, and then we have 2 half loops on either end. So that gives us 3 full loops, right? So that's the same thing as the third harmonic on the string. So that would make our wavelengths 2/3 times our length, okay? And so then the frequency of the third harmonic, okay, would be equal to 3 times V over 2L, okay? And so we can just stick with that, right? Or we can replace F1 as V2 over 2L, right? So it would just be 3 times our F1, right? Pretty simple, yeah? And then life gets a lot more exciting here, all right? So we can have a tube that's closed at one end, all right? Now this guy, because of the nature of this, where we've got an antinode and then a node at one end, remember the open end can be antinode and the closed end can be a node. All right, it has to be a node and an antinode like that, okay? We get a different experience here. And we get this as the harmonic series of our pipe with a closed end. And you notice it looks very similar, but there's a couple of distinct differences. Our length is multiplied by 4 in the bottom instead of 2. And then the other thing is our harmonic series is different. We can only have odd numbered harmonics. Okay, 1, 3, 5, 7, etc. We cannot have 2, 4, 6, 8. Only 1, 3, 5. So closed at one end, open at the other, we can only have these odd harmonics. Okay, so that's a little different. Oop. So let's draw a couple of these. All right, so we got F1 for our fundamental. All right, so there's this guy here. All right, but the difference is now it's closed at one end. All right, so open end is going to have an antinode, closed end is going to have a node, so we don't need anything in the middle here at all, right? Because it just needs to go from antinode to node, okay? So if we put another node in here, after this we need another antinode, and that would no longer be the fundamental, all right? So it's got to go from here, tall, and then it goes all the way across here to the node, like so, oops, like so, all right? So there's our guy. All right, ink color here, be red. So what's the wavelength then? Well, this is a little different, right? So how many loops do we have here? We have half of a loop, right? So it would take 4 of these to make a full wave, right? So the wavelength of the fundamental frequency is equal to 4L. And that's really where we get the 4L on the bottom of that, on the thing. Remember when we derived that equation before, right? This goes on the bottom. Okay, and so then the frequency, okay, of the first harmonic is equal to 1, right, because that's the harmonic number, times the velocity over 4L. Okay, now the next guy here, you might, well, the next harmonic we can do is not 2, right, because we can't have even harmonics. So the next harmonic we can have is our third harmonic, right? So once again, we'll have our pipe that's closed at one end, all right? So that's that guy. So this has to be an antinode, this has to be a node. So if we're going to go to the next harmonic, that means we'd have to have a node here and an antinode here. All right? So we'll go ahead and draw a dot here for our reference point when we're drawing our waves. Give me something to aim at. Okay, you're probably already used to the fact that I can't draw, so that makes it easier. So we got antinode, antinode, coming down to node, going to antinode, and then back up to the node. All right, antinode, through the node, up to the antinode, and then back to the node. So here is our third harmonic. Okay, looks just like that. All right. So the wavelength of the third harmonic, all right, the wavelength of the third harmonic, well, how many loops do we have here? Well, we've got one loop here and then half a loop here. So there's 2/3 of a wavelength right here. Okay, so that means that we'd have so let's just make ourselves a little math note. So we've got 2/3 of a wavelength is equal to L. So that means our wavelength would be equal to 3/2 times L, right? Wait, what did I do wrong? A fourth. Oh, they're 4/3. Wait. Node, antinode. Oh, not 2/3. Yeah, you guys should have stopped me. It's not 2/3 of an L. So it's a good thing I double checked it. It's not 2/3 of an L. My bad. It's not 2/3 of an L. We've got 3/4 of an L, right? Because 1.5 loops would be 3/4 of a wavelength. So we have 3/4 of a wavelength. So we need 4/3. There we go. That makes more sense. All right. So we have 4/3 of a length gives us 4/3 of a length gives us our wavelength. All right. And then the frequency of the third harmonic would be equal to 3 times the velocity over 4L. And then, or 3/4 V over L. Or we can plug this guy in again, right? And so you get 3 times F1. All right. And then let's do one more just for fun. Let's see if I can do it right this time. All right. So we got the fifth harmonic. So it goes down like this, and then like so. You got an antinode and a node. All right. So that means we need a node, antinode. Why did I draw an N? So I must be getting tired. All right. And then antinode. I did it again. Whatever. This time I won't erase it. Antinode. And then node. Yeah, then antinode. All right. Antinode, node, antinode, node, antinode, node. So it should have. Yes. Okay. So we got a node here. We got a node here. We got a node here. All right. Now let's draw our wave. So doing this, it's a lot more difficult than it looks. All right. So it goes up here, goes through the node, comes down to the antinode, through the node up here to the other antinode, and then hits the node. And you can notice that, like, these should be equidistant from one another, but you know, up to the antinode, down through the node, up to the antinode. Bingo. All right, so wavelength. Now these get, as you can tell, these get pretty complicated. All right, so let's think about this. We have 1, 2, 3, 4, 5 half loops. Yeah, 1, 2, 3, 4, 5 half loops. So we need 4/5 of, sorry, so 5/4 of our wavelength is equal to the length of the tube. All right, so this would be the fifth harmonic. So that means the wavelength of the fifth harmonic is equal to 4/5 of the length. Okay. All right, so then the frequency of the fifth harmonic would be equal to 5 times V over 4L. All right, and so this replaces would just be 5 times the fundamental frequency. All right. Now, so that works really well for for organ pipes because they're essentially just big long cylinders. Other wind instruments get more complicated, like flutes and clarinets, saxophones. You know, they all have keys and buttons, so they got different holes that go around alongside and inside of them, and so it makes the physics of these waves slightly different inside of them. Whereas Whereas organ pipes, they work, pretty straightforward, as well as, they have different shapes as well. Like saxophones, start really skinny and then they get bigger as they go out, and they get even bigger until they go out. Trombones, they start fat and then they get skinny as they go around the slide and then up here, and then they get fat towards the end, etc. And so this also changes the physics of these things. So like wind instruments can be pretty complicated as far as physics goes. So this was the most simple cases of these guys here. So let's do some practice problems. All right, so it says one string on a toy guitar is 34.5 centimeters long. What is the wavelength of the first harmonic? Okay. Well, we know from before that the wavelength of the first harmonic is equal to 2 times the length. All right, so that would be 2 times the length, but since we're human beings, we'll convert this to meters, so it would be 0.345. All right, so 2 times 0.345, 2 times 0.345. So we get 0.690, 0.690. The units would be meters for wavelength. Nailed it. All right, it says the string is plucked and the speed of the waves on the string is 410 meters per second. What are the frequencies of the first 3 harmonics? Well, we know generally, let's just jot down the formula. The frequency of the harmonic is equal to n times v over 2l. Okay, so the frequency of the first harmonic would be equal to 1 times the velocity, which is 410 meters per second, over 2 times the length. Now remember, the length is the length of the string, not the wavelength. The wavelength and length are 2 different things. All right, so it would be times 0.345. I really shouldn't have done this here because it'll cover up my answer. Oh well, divided by 2 times 0.345. So you get, oops, 2 times 0.345. There we go. So you get 502 sig figs, so 590 hertz. All right. And then frequency number 2, well, we could do it the same way. We could say 2 times 410 over 2 times 0.345. But that's way too much math, right? This is also equal to 2 times 590, right? Because we also have this other formula that the whatever frequency we're talking about is equal to n times the fundamental frequency, right? So 2 times 590, so that would be equal to so 590 times 2 become 1200, right, for our frequency here, and then F3 would be equal to 3 times 590. So 3 times 590 become 1800 hertz. All right, and that's what they got under there. Good for us. All right, sig figs messes things up. Watch out. All right, an organ pipe open at both ends is 34.5 centimeters long. What is the wavelength of the first harmonic? Well, the way open at both ends, the wavelength was still equal to 2L. So we'll get the exact same wavelength as we did before. All right, still 0.690 meters. Now, it's different when we talk about the frequency of the first harmonics if the air is 25 degrees Celsius. Now, remember, this means at 25 degrees Celsius, that's room temperature. So the speed of sound was 346 meters per second. All right, 346 meters per second. So that's our new velocity. So, all right, let's jot down our formula here to reference. Fn is equal to n times v over 2L. All right, so the fundamental frequency, F1, okay, should be equal to 1 times velocity over 2L, and our velocity is 346 over 2 times the length, which is 0.345. All right, so 346 divided by 2 times 0.345. So we get, how many sig figs? We want 3 sig figs, so it would be 501 hertz. And then to get F2 and F3, all we have to do is multiply this guy here by 2 and 3 respectively. So you get 1002 and then 1500. All right, and watch your sig figs here. These sig figs aren't quite right. This would really be 1.00 times 10 to the third hertz, right? If we were going to do sig figs correctly, this would be 1.50 times 10 to the third hertz. All right, okay. And then it says answer the same question if the pipe is closed at one end. All right, so this makes life a little more exciting. So remember, the wavelength of the fundamental frequency, okay, was equal to 4 times the length. So the frequency, or the fundamental wavelength, would be 4 times 0.345. All right, so it would be 4 times 0.345. So it would be like 1.38 meters. So that's the fundamental frequency, or the fundamental wavelength, etc. Excuse me. So now we got to find the first three. It says the first three harmonics. So we got to do F1. And remember, this guy only has odds. So instead of doing 2 and 3, we'll do 3 and 5 when we get to that point. All right. And so also remember that the formula for this guy, Fn, is equal to n times v over 4L. So it's slightly different. So it would be 1 times v, and it's still in air, sound in air, so it's still just going to be 346 meters per second. All right, over 4 times our length, which is our 0.345. All right, so you take 346 divided by 4 times 0.345. All right, so you get 250. 250. Whoa! Oh no. Oh no. All right. Oh, it does round up to 1, doesn't it? 251. 51 hertz. And then remember that we can't have even numbers, so it'd be F3, so it'd be 3 times 251, right? Which would give you 753 hertz. And then 5, this would be our F5 right here. All right, so this is kind of a long video with a lot of things to digest. So do your practice problems. Make sure that you can draw some of those those tubes on your own, those wave open and closed end tubes. They do take some practice, so they can be kind of tricky. Do lots of practice problems. Let me know if you have any questions, and I'll see you on the flip side.